our last seminar series of Spring 2021 of the AEESP AJAR Future Faculty Seminar Series. And we're extremely grateful for all of you who have joined us these past weeks in these seminars to celebrate the increasing diversity of our field through very outstanding presentations from our graduate students and postdoc. And while this is the last one for this semester, we hope to continue in the fall semester. We will select presentations from those who submit their mock faculty applications for the AJAR process through AEESP. And we will do this during the summer, and we will send information on how to do it and how to proceed soon, within the next couple of months. But we will submit information on time for you. And in the meantime, we see that some departments have follow-up, and they're picking up or organizing their own seminar series. And we have Adam Massman, and you can start sharing maybe if you want, who is from the Department of Earth Environmental Engineering at Columbia University, who is going to briefly talk about their seminar series and how you can present if you're interested in that in their department seminar series. So Adam.
Yeah, thank you so much for having this space. Yeah, so my name's Adam. I'm a graduate student in environmental engineering at Columbia, and I'm here representing a group of graduate students who are putting on a summer seminar series this year for early career researchers. And one of the main goals of our seminar series is to represent, the full breadth and diversity of perspectives that we have here in engineering. Kind of as a part of that goal, we didn't want to limit our invited speakers to folks that are already in our professional network. So we have a really brief application process for anyone who's interested in being a speaker. And I'm here basically asking for help spreading the word about this application. So if you wouldn't mind forwarding it to anyone who you think might be interested, that would be super helpful for us, and we'd be really grateful. I'll put some information in the chat. So we had also been advertising this as kind of a smaller department scale, more intimate seminar series, but some of our speakers might be interested in some more national exposure. So I'll also send out a link to anyone who might be interested in attending the seminar series. And for those speakers who want the national exposure, we'll open up those talks to everybody, and we can send out Zoom links. So just, yeah, thank you all so much for this. And I'm really looking forward to two great talks today.
Thank you, Adam. Well, now we're going to start the presentations, and we have two excellent speakers today. Our first presentation is by Dr. Jenny Zenobio. Dr. Zenobio studied sanitary engineering in the National University of Engineering in Lima, Peru, but then she proceeded to obtain her master's in aquatic ecotoxicology, looking at emerging contaminants in aquatic ecosystems, and her PhD in environmental organic chemistry, investigating the reductive degradation of PFAS by activated carbon supported by minerals from Purdue University under the supervision of Dr. Linda Lee. And I believe she's going to talk about her research today. She also worked as a research associate in Harvard University under Dr. Chad Vesitis, also looking at PFAS degradation using electrochemical filtration. Right now, Dr. Zenobio is a Chancellor's Postdoctoral Research Fellow at UC Irvine, looking at PFAS fate and transport in different systems. Dr. Zenobio has excellent publications and has received numerous awards, but I want to highlight, because the main goal of this committee is to highlight, promote diversity and inclusion, that she's a co-founder of an association that she created to encourage undergraduate students from her home university in Peru to pursue higher education. So with that, please, whenever you're ready, you can start sharing your screen, and I'm really looking forward to your presentation. Thank you.
Thanks. Let me, sorry. Could you see my screen, right?
We
Okay.
can see the second screen,
Oh.
not the main one.
I see. Okay, give me 1 second.
Yes.
Oh,
Now.
right now it's better?
Yes.
Okay, great. So, well, it's morning for me, but I assume for most of you guys it's already afternoon. So good afternoon and good morning for the ones that are in California. So my name is Jenny Zenobio. I'm a Chancellor Postdoctoral Fellow at UCI. Right now I'm a postdoc, but still working with some persistent organic pollutants. Today I will talk about destruction technologies to degrade this kind of chemicals, persistent organic pollutants that are in the environment by using nanoparticles. So the outline of my presentation, I will start talking a little bit about my research work and introduction about the research I will present today and the background. And what I'm proposing here and what I did is to work with emerging technologies for water treatment. And I will finish my presentation by key points of my research. So as Dr. Rodriguez mentioned before, I start my master here in aquatic toxicology, looking for the effects in pharmaceuticals and personal care products, specifically the effects on gene expression profiles in a specific organisms. And then I moved to environmental organic chemistry at Purdue, working with remediation technologies. Then I also did a couple of research and remediation at Harvard University. But right now my focus is in the social mechanism of different kind of emerging contaminants and their implications in the ecosystem. So with that, I will start talking about what are persistent organic pollutants. So those are not new chemicals. They are present in the environment for several years already. The only problem is that they are not degraded. So they are not degraded by biodegradation. They are very resistant to water treatments, and they usually accumulate. Right now, some of the most common persistent organic pollutants are PCB, DDT, and now the famous per and polyfluoroalkyl substance. That most of the people believe that the only way to degrade it is by incineration at very high temperature. So, but well, my presentation will focus today about PFAS. What are these chemicals? These chemicals are a group of, it's a family of chemicals that are present in the environment for several years. There are more than 4,000 synthetic organic compounds that have a carbon and fluorine atoms, which make them very resistant to any degradation process. The most common or the most stable are the perfluoroalkyl acids. Two of the most studied and also people doing research is in the perfluorooctanoic acid, the PFOA, and the perfluorooctanoic sulfonate, PFOS. But they are only two of them. So we have more than 4,000 that we still need to look in their absorption, degradation, transport, toxicity. So these chemicals are highly fluorinated. They have a different carbon change length from 2 to 16. They're hydrophobic and aerophobic. They're used for several commercial products like food packing materials, like in textiles, like in carpets, jackets. And that's how they are entered into the environment by indirectly by wastewater treatment plants. They have a lower sorption tension and because they are surfactants, and the main contamination in the environment by these chemicals is because it is used by aqueous film forming ponds. In areas where AFFF is applied, the concentration of PFAS can be in ppb levels, so very high. They are very resistant and cannot be degraded. But what is important? So what is important to study these kind of chemicals is because they are found in the environment, but it's also affecting aquatic ecosystems, birds, and different kind of animals, and also found in humans. In humans, they are found in blood, tissue, and also breast milk. It is also believed that they can be transmitted to babies when a mom is contaminated drinking, let's say, PFAS. The PFAS concentration can go to the baby. So the most study is PFOS and PFOA, and only EPA have like a health advisor for these two. The other PFAS, we don't have any specific limitations. So it's believed that PFOA is likely carcinogenic, and because of the chemical structure of all the PFAS, probably most of them or all of them have the same condition, and they are linked to several health effects like thyroid dysfunction. So these chemicals are found in surface water, groundwater, and also in drinking water. And as you can see here in the map, it is found in every state in the United States and also in different other countries. So that's my main goal, was to degrade these chemicals because they are emerging, they're in the environment, and they're causing health effects. But how we can degrade them? Because conventional water treatment are not able to degrade them. Some of them are able to remove them from different water matrix, but the degradation of these chemicals is still, there is still not enough information how we can degrade these chemicals. So we have to move for advanced technologies. My research, my current research and my future research, I want to focus on that in advanced technology for degradation of emerging contaminants that are very persistent. But depending on the chemical and physical properties, we have to look for different oxidation processes, could be oxidation or by reduction. So here's just a list of all the treatments that have been used. Most of them, as you can see, are oxidation treatments, which is not the best technology for degrade all the chemicals, all the emerging contaminants. It will work for a couple of them. So the reduction treatment is still very few process that is actually being established. So there's still just, most of them are just in batch study, lab studies, but they are not the current applications. So you can see here, one of the reduction treatments is cerebalent iron that is being applied as a reactive barrier. So with that information about the chemical treatments, we start to look which one could be possible to degrade these emerging contaminants. So we have right now absorption methods to remove PFAS from the environment, like activated carbon, the membranes, like ion exchange resin. But the problem of them is that with the absorption process, is just to remove the PFAS or the organic contaminant from the environment, but then you have to do another treatment, which will increase the cost of the process. So we need to look for actually real degradation in situ or ex situ technologies that can be cost effective and can be used in environments. So I'm showing here a couple of treatment technologies. For example, heat persulfate, permanganate, cerebalent iron, or vitamin B12. The two first are oxidation treatments, and the two others are reduction treatments. So all of them were tested by PFAS. We know that permanganate doesn't work for PFAS, so I will explore the other three. So heat persulfate is a strong oxidant and can be produce sulfate radicals, which will make the degradation of the organic contaminant. Cerebalent iron, we know that it's a strong reductant, it's low cost and very low toxicity. And vitamin B12 is also low toxic. Low toxicity is very low, so we can actually apply, but the cost could be a little bit higher. So looking forward, the heat activated persulfate tested by PFAS show degradation of one of the most common perfluoric acids, the PFOA. The degradation was happening only when the temperature is increasing. We saw a higher degradation at 50 degrees comparing with just room temperature. For PFOA, we don't have any degradation even at 90 degrees. So PFOA is not working with oxidation treatments, at least for heat activated persulfate. But what about with reduction treatments? So we mentioned before vitamin B12 be able to degrade organic contaminants. So it was tested by PFOS. You will see a degradation of PFOS, but the problem with vitamin B12 is only able to degrade one group of the PFOA family, which is the one that have like the less composition, only 30% of it, with the other 70% that is not still not degraded. So vitamin B12 have some good results, but it still need to be improved to have a complete degradation of the most resistant of this PFAS family, which is the PFOS. So then the other option was cerovalent iron. It's another reduction treatment. There is a paper published in 2006 that degrade PFOS completely, 100% mineralization of PFOS. But the problem with that is that they are using very high temperature, 350 degrees, and at very high pressure to be able to break down the chemical. So in theory, PFOS can be break by cerovalent iron, but we need to increase the reactivity of these particles to be able to have a complete mineralization at lower conditions or better conditions. So with that, I start looking for emerging technologies for water treatments. So I know cerovalent iron is applied right now in the environment, but nanomaterials is actually a new area that is emerging. So because they are more reactive, particles in the nano size are more reactive and will increase the degradation of some organic contaminants. I start exploring cerovalent irons, and I start adding catalysts to the treatment so we can improve the reactivity that we were getting just with cerovalent irons. So this nanocomposite that I create, the idea was to be a cost-effective treatment. So that's what I use, metals that are not expensive. It can be, have low toxicity, so we can actually apply in situ. But the problem with nanoparticles, so the advantage is they're very reactive, but the disadvantage is that they like to aggregate, which will decrease the surface area of the particles and will decrease the reactivity of this nanocomposite. So I mix new technologies, which is nanoparticles, with older technologies, so conventional materials like carbon activated carbons. So I use activated carbon to support the nanoparticles. So we actually avoid the aggregation of these particles, and we will increase the surface area for the reaction to happen. So as I mentioned before, we are combining new techniques with conventional process. Activated carbon is usually used for absorption. So we are dispersing this cerovalent iron first in the activated carbon flakes with just a solution of iron. So after the precipitation of the particles, the nanoparticles of iron, we start adding a catalyst, which will increase the reactivity of the nanocomposite. So with this nanocomposite, we were able to have a good dispersion of the particles in the flake of the activated carbon, as you can see in this TEM picture, and also in the SEM picture. We have a better dispersion, which we are avoiding the aggregation of the particles. The particles were in the range of 20 to 60 nanometers, which again, nanoparticles will be more reactive than particles of bigger size. So this work was actually, we get a patent actually 2 days ago for this work that is able to degrade PFAS. So we did a couple of kinetic studies to see how the degradation of PFAS is effective or not using this technology. We saw a complete mineralization of PFOS with the formation of inorganic metabolite byproducts like fluoride and sulfate. So after the SO3 functional group is broken, so we can see an oxidation forming the sulfate ion. So we saw a rapid degradation and generation of inorganics, and so when we tested if we are able to degrade both the linear and branch PFOS, because as you remember before, linear PFOS is around 70% and is found in the environment at higher concentration than branch PFOS. So we really need to actually break down the linear PFOS. And with this treatment, we were able to degrade both of them. So not only the branch PFOS, but also the linear ones. So the difference between linear and branch, I'm not planning to go in details about it, but I have backup slides if you want to know more. But the only difference is the branch PFOS have a different position, the CF3 group have a different position depending on where the carbon is located. So I start my experiment with temperature, so increasing the temperature, because at room temperature we don't see any degradation. So I start my experiment with 60 degrees, and then we start to go down to see if we are still getting some degradation. With 60 degrees, we have like 50% of PFOS degraded. Then we saw no degradation at 40 degrees, but 100% degradation at 50 degrees with a complete mineralization of the chemical. So we also study other PFAS. We studied the perfluoroalkyl sulfonates of different carbon change lengths from C4 to C8. The only difference between these two is the size of the molecule. So instead of have 8 carbons, a PFBS or the shorter carbon chain have 4. The same for the carboxylates. The other group, the perfluoroalkyl carboxylates acids, we also studied the molecules have or the PFAS have the carbon 8 or 4 carbons. So the difference between carboxylates and sulfonates is just the head. So the sulfonates will have the sulfonate group and the carboxylates a carboxylate group. So we test the particles at different temperatures as well and see that is whether the particles or degrade more PFAS with longer carbon change than with lower. So for the shorter carbon change for C4, it needs longer time to actually start degradation start happening. We saw a higher defluorination and desulfonation for the sulfonates comparing with the carboxylates. With the carboxylates, we saw just a few fluorine forming. With the sulfonate, the defluorination and sulfonation was higher. But with this technology, PFAS was able to degrade both of them, carboxylates and sulfonates. So again, we test different temperatures. We saw that for some of the PFAS, the degradation is higher at 50 degrees. For some of them, it's higher at 60 degrees. It's depending of the size of the chemical. And remember, this is a nanoparticle, so absorption is the first step in this treatment. So the chemical need to be absorbed to the nanoparticles to have actually reaction happening. So in lower, shorter carbon chain PFAS or organic chemicals have lower affinity or lower absorption capacity, will need longer time or will degrade less. So after degradation, because claim degradation or transformation of a chemical is very easily, we have to actually look for degradation products to confirm this chemical is degraded, not just showing a loss of the PFAS versus the initial concentration. So we start looking for degradation products. When I started my PhD work, there was not information about any degradation products. So the identification of the degradation products was like difficult, because we have to figure out what kind of reaction could happen there. We start looking for degradation products from PFOS and also for the other PFAS that we test very quickly. So we start looking for MSMS results and also confirm with the fragments that we are having fluorinated chemicals forming in the solution. So with that, we start looking for what kind of degradation product we can form. So we will have here is mostly the break of carbon and fluorine, or the break of carbon and the sulfur. So if we break the carbon and fluorine bonds, we can have polyfluoroalkyl sulfonates, because these nanoparticles are made in anaerobic conditions, so they're oxygen free. So the generation of the particles is mostly hydrogen by the dissociation of water. So what we are expecting is actually, if we break a carbon and fluorine bonds, is the replacement by hydrogen. But if we break the carbon and sulfur bond, we can, if we have a replacement of hydrogen, we were not able to measure this chemical, because the only way to measure is by not by electroionization. So with the break of carbon and fluorine, we will see a fluorine generation. And with the break of the carbon and sulfur, we will see a sulfate generation after the oxidation of sulfite. And the same will happen with the other PFAS. So we start looking for, again, all the organic intermediates that we can actually generate during the reactions. Many technologies can generate products that can be more toxic. So our goal was to be sure that we're not making the problem worse. We saw several organic products forming, but at very low concentration. So we'll see that even that some of them are forming, we are able to degrade it with the same particles. We have a complete mineralization of all the other intermediates as well. We also saw the formation of perfluoroalkyl acids during the degradation of PFOS. So the main mechanism here in the degradation of PFAS in general using these nanoparticles is by defluorination, breaking the carbon and fluorine bonds and replacing by hydrogen, or desulfonation or the carboxylation, which is breaking the carbon and the sulfonate or the functional group and forming the perfluoroalkyl carboxyl, the carboxylase group. So we also want to test if this technology can be applied in situ, because in the lab, everything is like in perfect conditions. Using DI water, they have nothing there that can interfere with the reaction. So we start using groundwater to see if the reactivity of the particles can be affected or not. So with groundwater, we'll see, we actually saw a degradation actually decline for all of the PFAS tested. We use a groundwater from a former fire training area in Massachusetts, which have PFAS in the water. So the higher concentration was for PFOS, of course. But using the nanoparticles with groundwater samples, the degradation was lower than with just DA water samples. But still, we were able to degrade PFAS. But what was actually strange here is that we saw like a generation of other perfluoroalkyl acids that could be by the generation of the presence of PFAS that were not detected before, like the precursors. So we move forward to see if this technology, okay, it can be used with groundwater, but what about if we want to use like permeable reactive barriers? So we need to test colon studies. Right now, they are testing in my old university colon using sand in combination with these nanoparticles to see the effect if these particles are effective for treatment in using reactive permeable barriers. So we still see degradation of PFAS, but the degradation is lower than DA water conditions. The formation of fluorines is still observed, and also the generation of other organic products. So with that, I will make just a quick summary of what we found. We were able to transform these emerging contaminants 100% using the combination of two process, nanotechnology with all absorption treatment, which is activated carbon. This combination was able to degrade these emerging contaminants, and also not only one of them, but a couple of the families of different carbon change length. We saw a formation, and we proved that this chemical is degraded by the formation of inorganic and organic compounds. So the problem with the degradation of these chemicals is that they have a different absorption capacity. So that if we have higher absorption to this nanocomposite, the degradation will be higher. And that's what we saw, lower degradation for compounds that have less absorption. And we will really believe that this technology can be actually improved to be able to be applied for ex situ or in situ applications. So with that, I'm finished my presentation, and I don't know if you have any questions.
Thank you so much. I was just posting in the chat that if you have questions, please raise your hand and I try to call your name. Yes, we have one. Thank you, Kevin, I think. Please can unmute yourself and introduce yourself and ask your question. Thank you.
Yeah, and I'm Denjun, an assistant professor at Auburn University, and yeah, so that is a very interesting presentation, trying to combine the iron with nickel on the activated carbon, try to degrade the PFAS. So I think my question is that so in theory because I think this is a reduction process to degrade the PFAS, right? But the standard reduction potential of iron, the zero valent iron, is minus 0.4 voltage, while the carbon fluorine bond, the standard reduction potential, is up to minus 2.7 voltage. So in theory, you cannot only use the iron to reductively degrade the PFAS. I'm not sure, did you use other treatments like the UV radiation or other processes in your
yes, so we test different conditions. So I can actually have a slide of that. Let me show you. So we test different conditions. So just nanoparticles of iron at room temperature, we don't see any degradation. We test increasing the temperature just with iron, we don't see any degradation. We start combining different conditions like adding catalysis, increasing the temperature, and also dispersing the particles. So that's the why actually give us the best conditions for degradation. By just iron, PFAS is not able to degrade at all.
But in one of your figures, you showed that you detected the fluorine in your compound, right? So because
right. Yeah, but if you see here in the figures, I'm showing you just iron in combination with temperature and also with activated carbon and catalysis. The best conditions is activated carbon with a catalysis and a higher temperature. Without temperature or without catalysis or without activated carbon, the degradation not happen or is very little.
Yeah, so basically, so right now, I think most of the people, they think that the hydrated electron, which has a very negative standard reduction potential, that has a chance to degrade the PFAS. But I don't think the iron will do a good job. But maybe other mechanisms involved in this degradation processes. Thank you.
Any other questions? I think that if we don't have more questions, we can always ask them. And if you think of those after our second speaker's presentation, but at this point, we are going to move on. It's already 12:35. And I think that Jeremiah is going to introduce Quay.
Absolutely. Thank you, Lucia. Thank you, Jenny.
Thank you.
So Quay, I'll just give you a second to get your slides up and then I'll start with the introduction. There we go. Okay, hi there, everyone. My name is Jeremiah Johnson. I'm an associate professor in environmental engineering at NC State University. And it is my great pleasure to introduce the final AJAR seminar speaker, Amanda Quay, who is currently a PhD student in civil and environmental engineering at Stanford, working with Professor Megan Motter. Quay's research focuses on behavioral responses to environmental and policy changes in agricultural systems. Their current projects include in-depth investigation of food, energy, water system interactions at multiple levels of spatio-temporal resolution. Quay earned a BS in chemical engineering from Stanford, master's degrees from Yale and Carnegie Mellon, and an NSF graduate research fellowship. And somehow Quay also found time to do internships at the CIA as well. Despite being just in their 4th year of their PhD, they've already published several articles in top journals, including Environmental Science and Technology and Environmental Research Letters. It is my great pleasure to introduce our final speaker, Amanda Quay. Quay, the floor is yours.
Great, thank you, Jeremiah, and thanks, Jenny. It's always good to hear about the hot talk. Go ahead and get started. All right, so agriculture, I consider it the original engineered system. It's got a lot of interesting sustainability questions. So how do we motivate sustainable food, energy, and water nexus practices? Well, policy is designed to drive change, but we also know that environmental change or environmental disasters can drive behavioral change. However, economic models often suggest that environmental externalities may end up being poorly represented in growth. A really great example of how environmental changes might not drive sustainable practices in the California CV, Central Valley. So in the most recent extreme drought of 2014 to around 2017, food and duration. So you can see in the red here is basically the severity of the drought and how much it fills up. The y-axis is how much of the state is in that drought period. And so you might expect that you would have lower yields and lower revenue from high water intensity crops like almonds. But the blue here shows that you actually see the opposite, and there was an increase in saleable almonds over the drought period. So growers are achieving this by relying on groundwater instead of surface water to make up for what they're missing. And that's really a gamble for them. They're taking short-term economic benefits, but they might be sacrificing the long-term health of that field. So unfortunately, there are reasons that environmental drivers may fail. But we, as policymakers, are trying to design and drive good change. And in order to accelerate transition to sustainable agricultural behaviors and ensure a long count for feedback loops and complexity in underlying and integrated policy, economic, and environmental models of agriculture. So my dissertation centers around this vision of better accounting for how a change in one of these models can have reverberating effects throughout the integrated system. And trying to overcome some of the domain silos that have led to incomplete extensions, basically, across the policy, economic, and environmental models. So rather than, for example, having economists over here modeling behavior of human agents, but stopping short of really linking those decision-making models to environmental models, but then also having natural systems modelers on the other end, incorporating these really highly detailed environmental feedback loops into their yield models, but making some behavioral assumptions that overcome some of the complexities in the behavioral space. I'm trying to meld those two together. So today I'm going to talk about two projects, hoping to at least somewhat convince you of this vision. The first project is using some large, messy data sets with high resolution to try to eke out really small shifts in grower behavior. So my work focuses on the California Central Valley, and this project is about soil salinization, which, if you haven't heard of this process before, it's anthropogenically mediated. and it involves dissolved salts in irrigation water, reducing agricultural yield productivity. So how much does that lead to damages? A regional annual damage estimate estimated that it was about $1 to $2 billion of annual income loss. Another student from my lab who came before me, Paul Welly, did a higher resolution estimate using satellite-based crop classifiers for more spatially explicit damage distributions, and then aggregating that data upward to get a more accurate overall report of net damages closer to $4 billion. One of the key points here is that remote sensing data and high resolution data enables aggregation of high resolution information to a scale that you're interested in and decreases the bias in your analysis overall. But Paul had to make one pretty critical assumption that everybody else in this field when doing damage estimates has also made, which is assuming that growers are not adjusting their cropping practices as the environment changes. And so I was curious to what extent that might be true, because you would expect that growers would adjust as their yields are dropping, right? So in a profit maximizing rational case, you would have some economic model that would imply something very different. So in this graph, you have maybe a parcel of land and something really high value like almonds might be the most profitable option until soil salinity increases to the point where you have a drop off in how much yield you're actually able to produce. That's drop off in relative yield. And then it's actually going to be more profitable to plant something that's more resilient to salinity per unit. So I looked at crop switching at a field scale between 2014 and 2015. And you can see here, this is basically a Sankey plot with all the different crops that I was looking at. The box width is basically how much cropland is in that crop, and then any switches will be observed from the left to the right. And yeah, like you are seeing changes here, and it's detectable over a short time period. You actually, I've ordered this in top to bottom for increasing salinity tolerance. So fallowing a field is for obviously the most tolerant of a salinity because you're not growing anything on it. And remember, I showed the plot of that extreme drought earlier. One of the reasons that very high pressure, we're looking at these years in particular, because you can really see changes during a drought year where they're using and relying on groundwater increasingly, which often drives up the soil salinity in the system. So my goal in this project was to understand and differentiate between the importance of different drivers leading to crop switching. So here are the explanatory variables that we're accounting for while trying to understand different drivers and their relative importance or weight. The dependent variable here, our behavioral outcome, is crop choice. I gathered the top 20 crops according to gross revenue for 19 counties in the Central Valley. And one of the things that we do by using 2 years adjacent to each other is we can keep data for a land parcel tied together between those 2 years, so that if a policy or environmental factor that's not explicitly counted in this set is appropriate to leave out because we assumed there wasn't a change between those 2 years, this helps kind of combat any potential limited variable bias. But it's important for us to think about the fact that, you know, these are all from different sources. Some of them are remotely sensed. Some of them are like county specific price and expenses reports. So environmental parameters are often realized at scales very different than economic or behavioral parameters. And so we want to make sure that we're making good use of the wide range of data resolutions here. So to do that, we estimated 2 different models at 2 different scales. One at the scale of the environmental variable that we're interested in, and then one at the economic and behavioral outcome. So our first model uses resolution of the environmental variable we're interested in. Apologies, I'm seeing that my connection's a little unstable, but that's work from home life. The second model uses a resolution much closer to our economically driven outcome. So let's look at this first model. So of the 18 crops plus fallow land in this regression, 12 had statistically significant crop salinity interaction coefficients. And so when you look at this figure, you have the crop salinity interaction on the y-axis, and then on the x-axis, you have the 50% yield salinity, which is basically a metric trying to combine the fact that every crop has a threshold at which salinity starts to impact their yield, and then a linear slope for how much decline you'll see for every additional decisiemens per meter of salinity that you add to that soil. And the interaction coefficient is trying to explain if you add an additional unit of salinity, what is the probability that you're going to have an increase or a decrease in a particular crop. So you're seeing that in the gray here, those are coefficients that had an insignificant significance coefficients. I'm using a cutoff of P at 0.05. We can discuss whether that's useful or not later, but the trend here generally makes sense for these average marginal coefficients with the correlation of 0.62 for the significant terms, which supports the hypothesis that salinity is an observable environmental driver of land use change and that grower behavior. So next I wanted to see if we could bolster that observation now at the scale of our economically driven outcome, which is that grower crop choice. So we had to reduce the crops included in this model just to manage computational complexity, but we're still accounting for, I think, 84 or 85% of the soil polygon acreage composing the first model. And generally, the trends that I described already held in this new model. This specification was really useful to us because it also enabled scenario analysis. So if we monotonically vary soil salinity across the study area, what does this model predict will be the crop distribution and crop selection for each field? So that's exactly what we're looking at here. On the x-axis, you have our monotonic change in salinity across the area. And then on the y-axis, basically the study area's aggregated crop shares for the crops that we include in this study. And you can see that with almond prices so high, we have a really unrealistic boost actually in almond acreage. You're not seeing 30% of fields in this region planted as almonds, but I think what's interesting to look at and maybe more realistic is that almonds are very sensitive to salinity changes. So you have a really steep negative slope as the salinity increases. And then you'll see something that's more salt tolerant, like hay, will overcome crop acreage over time because it is less sensitive to salinity. And then fallow land obviously is a great catch-all, especially in drought periods, because it adds an option value to growers. So they get the option of not committing to a particular crop, especially a tree crop that has many years of life in it, and letting the uncertainty of that drought and associated potential salinity issues resolving before you make a commitment. So next we aggregated revenues for the scenarios. The model that I built is this modeled crop switching in blue. And then we're comparing it to the assumption that's been made in previous studies that you would not allow any crop switching, and that's in red. And so as you aggregate revenues, of course, you're going to have a drop in the revenue as salinity increases, but that drop is much smaller than in the fixed crop assumption. So this really illustrates the value in growers switching their crops and also highlights the inaccuracy in making that previous simplifying assumption for faster or simpler environmental damage estimates. All right, so I just want to remind you, those were aggregated results. This model is field resolved. This is Fresno County and field specific damages in the same two scenario options. And I just want to highlight that this helps us create targeted and cost-effective policies. So pinpointing where farmers will be most impacted, but also quantifying the extent of investment so that your benefits overall can overcome costs associated with an investment. So that can be helpful for taking damage assessment maps to inform decisions about state level investments, whether it's specific interventions like buying land back for conservation. This is a pretty common one in California. Or offering subsidies for types of water quality management systems that other wonderful environmental engineers are thinking about building. Or something more abstract. So we know that policymakers are keeping this in mind for their new groundwater policies. They're thinking about enhancing state monitoring and enforcement of groundwater withdrawals. Because guess where all this water for crops is coming from in a drought like this one? It's overwhelmingly groundwater. It's about 43% of irrigation in the Central Valley comes from groundwater in a typical year, but it's upwards of 70% in a drought year. All right, so when we think about these problems, we want to really keep in mind that we want to have a way to manage these strong drought issues. This figure is the GRACE satellite. You might be familiar with it. I think it graced the cover of a science magazine recently. And so you can see the extreme drought in this region leading to huge drops in groundwater storage. So due to this, representatives signed the Sustainable Groundwater Management Act, which I'm now going to call SIGMA because that's a mouthful. That was signed into law in 2014, and it's starting to come into effect right about now. COVID made it a little harder, but one of the things that's unique about this law is that it's, for the first time, allowing creation of enforceable groundwater regulation to manage groundwater withdrawals. One problem, though, is we don't have great actionable information about current groundwater levels, especially not at the temporal resolution that's relevant, and not with uncertainty ranges, which are very useful for policy analysis. So this is the Department of Water Resources, or DWR. I'm going to be using that acronym a lot too. So DWR maps groundwater depth 2 times a year over a limited range of the groundwater basins. And so they only do that in the months where sampling is highest. And this drops a lot of sampling over the course of the year, which is really reducing the richness of these very expensive collection efforts. And it obscures month-to-month variations that help us understand what's being grown and how growers are behaving. So one thing that we need is higher temporal resolution. It's also lovely to try to improve the uncertainty intervals around this data. Policymakers really need ways to see the degree of confidence with which environmental systems are being represented to them, especially because that helps roll out policy on uncertain data with greater confidence that you're still within a reasonable range. So my last project that I talked to you about was all about field scale resolved adaptation. And now I'm going to talk about the benefits of using statistical models to capture environmental uncertainty. And this project really focused on that higher temporal resolution instead of just spatial. So what we did to try to improve these DWR maps is we built monthly groundwater depth ramps with predictive intervals, calibrating a Bayesian hierarchical model using our understanding of underlying environmental mechanisms. So hydrology about groundwater level variations. So quick project roadmap, we collected this publicly available data, and then we instantiated a Bayesian hierarchical model using an MCMC algorithm to get a posterior distribution of our parameters for the model. And then for every missing reading, that's month to month or in a particular grid cell of our map, we imputed the missing reading 100 different times to get a portfolio of potential interpolated groundwater depth maps. Next, we did some internal validation just to make sure that the model made sense, and then external validation, which was really just comparing it to the status quo maps. So just an example of the types of products that we built out of this that were very useful in that first project's model when we needed to include groundwater as an explanatory variable. We've built these monthly groundwater depth ramps, and more importantly, we've also included a predictive interval. This is for 3 counties in the Central Valley, just as an illustrative example. And so this 95% prediction interval can really enable sensitivity analysis for models using groundwater as a variable in their analysis. Comparing it to the DWR interpolated product that we kind of started this mini project tangent on, you can see that our maps are generally consistent with each other, but because the Bayesian hierarchical model takes advantage of spatiotemporal dependence from month to month, instead of just taking samples from one month versus another month, our map can cover a much larger area. And so when we intersect the per pixel difference between the DWR's layer and our model's mean prediction, we get a map that looks like this. So basically, if you see a cell that is white, it's a perfect matchup. And then the green and purple are above and below that perfect matchup. And 95% of the cells in this region were within 5 meters of an exact matchup. So pretty consistent. Okay, we're 22 minutes in. In conclusion, I've covered 2 projects that really illustrate how expanding integrated models for agriculture and for other complex fused systems that we face as environmental engineers requires a solid background in leveraging very large data sets. I mean large both in terms of volume, which is the way we might think of it first, but also in data variety, velocity, and veracity. And I've also demonstrated that we can apply more interesting, maybe more computationally expensive statistical tools to glean insights from that data. But I want to make a quick note here that I think it's tempting to talk about this and be like, ooh, big data, data-driven, and talk about these extensions in a way that discounts, the underlying science or the value of a good, simple model. And so I just want to point out that, we're an environmental engineering community, and I really think that when you're looking at quote unquote big data, data-driven work, there's a lot of value in taking our strong environmental engineering domain knowledge and understanding of the underlying systems, and then using those to make really thoughtful decisions about whatever computationally intensive practices we want to pursue. And there's a lot of value in that iterative feedback and cooperation with experts in the data space and experts in the environmental policy space that we might be more familiar with. So as I wrap up my PhD and I look to future research, there's a lot of interesting questions around integrated agricultural models. So questions around overcoming environmental data gaps for things that are very difficult to observe, like groundwater irrigation behaviors. How much is a grower relying on surface water versus groundwater on a year-by-year basis at that high resolution? Or what can we do to take our understanding of what an environmental driver looks like in creating change? And how can we use that to predict the impacts of novel policies in a field that has very little groundwater policy at the moment, but a lot of potential enforcements coming down the pipeline? So with that, I really appreciate everyone being here on a Friday morning or afternoon, depending on what time zone you're in. And I hope we have some time for questions.
Thank you so much, Quay. That was an excellent presentation. If anyone has a question, please raise your hand. I'll take the liberty as the moderator for you to lead with a question. And I was thinking about the relationship that you shared on the salinity and the evolving crop shares. And I was wondering if you had any thoughts on how the lead time for crop production or the longevity of the crop stock interplays with that relationship. You know, for example, the almond crop takes, you know, half a decade to a decade to reach maturity. You switch to potatoes and you can have a mature crop in a matter of months. So as folks are considering switching their crops, the lead time to both start an almond crop, but ultimately to give up an almond crop, it seems much more severe than some of the quick to maturity options.
Yeah, big agree for me. Yeah, what we're talking about here is basically the difference between annual and perennial crops, right? And there are some crops that take a much longer time to grow to maturity. And so we did some modeling on this project around the concept of sticky crops, quote unquote. So one of the things that we find is, yes, the tree crops, you see switches in them less often. But I think it's also important to think about what this looks like on the side of the decision makers. So in an irrigation district, when they're making decisions about how to allocate surface water during a drought period, they're going to upset growers who have one of these crops that'll be very expensive to try to regrow. And they're going to have to prioritize water allocations for those almond farmers rather than someone who's growing something like strawberries, where you can basically start over and be ready again in 2 years. So.
That's great, thank you. Any additional questions? Okay, Adam, please.
Yeah, thank you so much for the talk. I really loved it. Yeah, so I guess, so my question was, and this is not my area, so this might be completely false or wrong or whatever, but so like I was curious about, like, are there some feedbacks with you know, decision makers' decisions that if you integrate over enough time could kind of change the story? Like, I'm kind of thinking of, like, you know, like, is there anything, can anything happen where, like, okay, let's say you switch to hay, and then that switch to hay has an impact on the salinity of the soil in the future in some way, that then causes, you know, the future to decision making to change. And if you integrate over some, you know, longer or shorter time horizon, that adjusts, I guess, like your revenue from your crops. And I guess, like, are the decision makers, does it seem like they're making decisions over shorter or longer timescales? And how does that all relate? I don't know. Do you kind of get what I'm trying to say? I'm not doing a very good job explaining it, but.
Yeah, I mean, you're getting at very big questions that take, that I haven't been able to, like, fully parse out either. But, you know, there's limits to what we can control in the type of market that we've set up. And so, you know, almond prices going up during a drought year made them a very attractive option, right? And I think that we just, we need to pay attention to what actually makes sense to attempt to control or regulate, and focus on creating metrics and outcomes around those specific things that we know we really care about as decision makers, instead of trying to control the entirety of all the feedback loops. I think accounting for them is useful, but we can't control them all, right? I don't know if that was a great answer, but happy to talk offline or kind of expand further if that helps.
No, that's great. Yeah, thank you so much.
Thank you, Quinn. I think that's a great segue to our informal few minutes that we usually preserve at the end of these sessions. And so with that, let's all give a virtual round of applause for both of our speakers. And I think we really ended on quite a high note here, two stellar presentations. If our speakers are willing to, and anyone is interested, we can keep the Zoom room open until 15:15 for a more formal Q&A or just an opportunity to say hello. So anyone who's interested, turn your video back on and we can we could turn the recording off and just have a more casual end to the session. Thank you.